Okay, so hi everybody. Welcome to our weekly seminar. Today we have the pleasure to have a speaker from the house. So a few words about Ethan. So Ethan completed the PhD in last July 2024 at the Wayne State University in the US, advised by Edward Cato. Ethan leads the spectral analysis of multiple X-ray bright active galactic nuclei using NICER, an X-ray observatory aboard the International Space Station. Their work was part of several large-scale multi-wavelength reverberation mapping experiments using space and ground-based observatories. And then finally, last October, Ethan began working as a postdoctoral researcher in the group of Maria Carisi here at the Institute in where they will conduct a time domain optical search for supermassive black hole binary candidates using quasar light sources. So welcome to the Institute.
Thank you. Yeah, so hi everyone, I'm Ethan, and today I will be talking about my recent work studying the connection between individual X-ray spectral components and ultraviolet emission in AGN using an X-ray observatory called NICER. And my screen seems to be frozen. So that's not good, but I guess I can just click on things. Yeah. Excellent. Okay. I think maybe yeah, it's the presentation for some reason. And then I'll just try to share. Yeah, I think that the Zoom is just gonna get the presenter notes version. There's not really anything interesting in there. Okay, there we go. And back on track. So the work we're doing is called reverberation mapping, and it is the optimal way to study the geometry of active galactic nuclei that are too far away to be spatially resolved with things like radio interferometry. All of our telescopes are pointed at the same point in the sky, but due to the properties of our accretion disk, which starts as some sort of gas flow, as it moves towards the black hole, the interactions with neighboring particles will produce friction that will heat the accretion disk. And then as that energy is radiated away as thermal emission, the objects will move closer towards the black hole. They will move faster because they're on closer orbits, and they will get hotter. And so the black body temperature will start to increase. And this means that our wavelength of peak emission will increase as we get closer to the black hole. So in our geometrically thin, optically thick accretion disk, When we observe at optical wavelengths, we expect to be targeting the outer part of the accretion disk. As you move closer to our black hole, you'll start to emit an ultraviolet. Eventually, you get this far ultraviolet region that we can't observe due to absorption from intervening gas. But then you start to get a clear spectrum again as you get into the X-rays. In this region, we think that the disk has now broken up, and this material is now a free-floating region called the X-ray corona. You have these free-moving electrons that reach temperatures much higher than what you get in the thermal standard geometrically thin, optically thick accretion disk. And in our spectral energy distribution, this really manifests as two different features. So in red here, this is an X-ray SED. This is the energy of the incoming photons. These little black ticks are actual observations in the UV optical down here, and then the X-rays. And then this is flux normalized based on the energy in each bin. So there is this sort of bump. This is the composite of all of the black body emission from the disk. And then you have this power law that extends up to energies of about 100 keV. So this is much hotter material than could be obtained in this viscous accretion disk. What this means is that we're experiencing, or we're seeing the effects of inverse Comptonization or inverse Compton scattering or Comptonization. Basically, the seed photons from the disk will interact with this cloud of very hot electrons. The seed photons will be upscattered to X-rays, and the electrons will lose energy. This produces our power law spectrum. And then we now have these X-rays that are being re-emitted. And the X-ray processing scenario suggests that those X-rays will then reach back to the accretion disk. They will be absorbed by the material in this optically thick disk. They will then increase the temperature in that region, and you'll get a higher flux from the black body in that band. So we call this reprocessing in short. And the interesting thing that we would expect to see with these light curves is that the X-rays are highly variable on timescales of minutes to days. You'll see these peaks where it gets really bright by like a factor of 2 or 3 and then drops down the next day. And if you see this peak in the X-ray light curve, that means that some light travel time later, corresponding to the distance between the black hole and the region of the disk, you would expect to see a peak and then a drop in the ultraviolet light curve, and then the optical. And we can do something called a cross-correlation test, where you shift the light curves relative to some reference band, and at some time shift or some lag, you get an optimal correlation, where the light curves start to match up due to this central reprocessing. Now, this has been tried in dozens of AGN using ground-based optical monitoring, UV space telescopes, and SWIFT, the X-ray space telescope that was kind of the predecessor to NICER in these monitoring capabilities. This is for a long time, this was the only X-ray telescope where you could reasonably take a snapshot of an AGN every single day, and you could get count rate measurements, photometry measurements of the hard and soft X-ray fluxes. And when you start to do these cross-correlation tests on these AGN, you notice that the UV and optical, here this is the wavelength and this is the lag with respect to the reference band. The UV and optical are actually pretty well correlated, with some caveats that the people doing things like broadline reverberation will be studying and getting into. And then the X-rays, which are supposedly driving this whole train, look kind of bad by comparison. The X-rays are often poorly correlated, much less so than the UV and optical light curves. And the lags are often too large to be physically reasonable for the size of this accretion flow. So in an AGN like NGC 5548 and NGC 4151, you have the hard and soft X-rays with lags that are much longer than the prediction for these geometrically thin, optically thick disks. A negative lag here indicates that the X-rays lead the UV by like 4 days or 2 days, depending on what band you're in. In some AGN, the X-rays, which again are supposed to be driving this variability in our standard picture, we expect them to be driving it, but they're actually lagging behind. So we're very limited by what SWIFT can observe, because SWIFT is only getting these broadband count rates. It's not very sensitive to the individual parameters in some sort of spectral model for your X-ray emission. And it turns out that there is not only emission from an X-ray power law in these AGN. There's a couple other features. A notable one that we probe with this research is the soft excess. So if you fit an AGN spectrum in the X-rays to a power law, this is what you expect from repeated Comptonization in an optically thin corona. If you fit an AGN like NGC 7469, here again is the photon energy, and then here's the counts per second, the count rate on the detector normalized by the, or divided by the energy in the bin. If you take this spectrum, this was based on an XMM Newton observation of NGC 7469. You fit the spectrum above 2 keV in the hard X-ray band or the high energy X-rays, you'll get a very nice fit to a power law. And then when you look at the full spectrum, there's this huge residual below 2 keV that we call the soft excess. This is present in many AGN, and there's a few possible origins for what could physically be producing this emission. The first one I'll talk about is relativistic reflection. Basically, you have this ionized inner disk. The innermost part of the accretion disk is getting this heavy amount of X-ray flux. And so you're going to get a bunch of ionization lines produced as the X-ray corona is incident on this disk. This disk is also moving very close to the speed of light. It's very fast, and so it's going to get blurred. In the soft X-rays, you end up with this suite of ionization lines that becomes this nice smooth spectral feature. And then in the hard X-rays, the really great predictor of, or a really great indicator of ionized reflection is the iron K alpha line at about 6 keV. Unfortunately, with NICER, after about 6 keV, our background count rate, this black line here shows what the background is doing. It gets pretty comparable to our source count rates. We're not great with constraining the parameters of the broad iron K alpha line in our models of these AGN. So we just focus on the soft excess for our work with NICER, but previous studies have been used to constrain the size of the inner accretion disk using this iron K alpha. Now, the other option that we have here is the soft excess that we explore. That is, that the soft excess could be produced by this warm corona. Essentially, if the inner accretion disk fails to maintain thermal equilibrium, you'll get this layer of electrons. It's been predicted that this layer of electrons will kind of leave the surface of the accretion disk. They'll have much lower temperatures than the electrons in the hot corona. KT for the hot corona is typically around 100 keV. This is about 1 keV. So we call it the warm corona. And it is going to be subject to anything that is going on with the inner accretion disk. In these AGN, we see these fluctuations on timescales of hundreds of days that are various AGN. NGC 5548 is a really famous one. Ferrol 9, the first part of our campaign on Ferrol 9, has a really big fluctuation in the disk. And when you see these fluctuations in the disk, they're often not accompanied by a fluctuation in the hot corona. So models of, say, intrinsic temperature fluctuations that are moving in and out in the inner disk, we think might cause these. So if we see, our hypothesis is basically, if we see a very strong correlation between the X-ray power law and the soft excess, this tells us that we're likely seeing these ionized reflection lines. The X-ray corona gets brighter, the soft excess gets brighter. But if in our AGN, the disk is doing these slow temperature fluctuations on hundreds of day timescales, and we don't see that in the X-ray power law, but we do in the soft excess, that's a really good indicator for a warm corona. And this type of study can only be done with one instrument, NICER. NICER is sensitive to the changes in the spectral parameters at timescales that they actually vary on, at least 1 day reverberation mapping timescales. The other spectral feature that we have to contend with in our AGN is absorption. So if you put intervening gas in between the X-ray source and our telescope, it will diminish the soft X-ray flux. The neutral obscuration, where there's not a super bright X-ray source right next to the gas, tends to produce this continuum. And then as you increase the column density, right, this is an unobscured flat power law with an index of 2 in black. And then as you increase the column density to 10 to the 21 per centimeter squared, or down to the Compton thick regime, 10 to the 24 per centimeter squared, you end up with a total loss of your soft X-ray flux. This is a problem if you're trying to measure the soft X-rays in your soft XF, obviously. The other feature that you can get is absorption with an ionized obscurer, where the gas is close enough to the ionizing source, or the ionizing source is luminous enough that the gas ends up reaching this kind of stable level of ionization, and you get these prominent lines that start to appear. High resolution X-ray spectroscopy like XMM Newton is great for characterizing the properties of the gas using this. And with NICER, as I'll show, we can pick up on these bold changes in spectral shape caused by obscuration. With NICER, specifically, the way that it works is it has the largest counterweight of any telescope I'm aware of. It's aboard the ISS. It's not a focused optics system, so you don't get a picture of your image. You just get photon count, photon arrival time, photon energy with pretty decent precision. This allows you to make these spectral models that account for absorption, emission, all of these things. And it is the only other X-ray observatory that has the flexible scheduling capability of SWIFT, where it can re-observe these AGN every single day for 300 days or longer. The problem with NICER, the big caveat is because we don't get an image of our source, you can't do your simple background subtraction by just taking a region that's not contained within the AGN. So you have to do an estimate or a model of the background based on things like the amount of high energy particles in the region where the ISS is the space weather, so to speak. And we'll talk about that going into this as well. Two of my papers have very detailed appendices on the NICER background, so if you're really curious about that, I'd love to chat with you about those. The first campaign that we do is the Active Galactic Nuclei Space Telescope and Optical Reverberation Mapping to AGN Storm 2. This is on Markarian 817, and it was chosen because it historically is a very clean, unobscured view of the center of the AGN. As of 2018, there was very minimal line of sight obscuration, so it was supposed to be a really great target to see the dynamics of the X-rays and the interaccretion flow. It was also the successor to the campaign on NGC 5548, which was unobscured, but then the campaign started and it became obscured. This complicated a lot of the reverberation measurements. And then, of course, you can put your telescopes in space, but you still can't control the weather. And in 2020, when we started our campaign, we found this brand new obscure. This was especially prevalent in the ultraviolet spectra. This is an HST cost spectrum from 2020 in blue, and then this overlaps with spectra from the previous decades. And the biggest feature that you can notice is at around 1600 angstroms, there's this broad carbon-4 absorption trough. That's new. The silicon-4 absorption trough is also super prevalent. All of these little features pointed out here in blue are various absorption troughs. They're all blue shifted. It's especially noticeable with the carbon-4, and this is consistent with an outflow, something moving towards our line of sight. And the measurements of the ionization state of each of these lines is consistent with an obscure around 3 light days from the central black hole. This is kind of co-spatial with where we would expect the broad line region to be, the free-moving gas that's producing things like this broad carbon-4 line. So with the X-rays, we also see even more dramatic obscuration. This is an X-ray light curve of our full campaign on Markarian 817. There's actually about 3 years of extra data that have been gained since then. The NICER PI has granted us a legacy target status with Markarian 817 because the behavior is just so odd. They want to watch and wait. We all want to watch and wait, see if this wind is going to change. It showed up within 2 years, so it's clearly happening on human timescale. And when we looked at it during the campaign that is in my first paper, though, we see that we're usually at about 10% of historical brightness. And then there's this flare in April of 2021 where we briefly reach historical brightness for about a day. Purple is the NICER count rate, and then green is the SWIFT count rate. You can see that they overlap. The telescopes are seeing the same thing, but NICER has a much higher count rate sensitivity than SWIFT in spectral modeling. Because of this, NICER was actually key to understanding what was going on with the X-ray light curve here. We can see just from basic photometry the hardness ratio, the spectrum is becoming softer. There's more soft X-ray emission during this flare. But that's not sufficient to tell us really, is this the X-ray corona that's getting brighter? Is the obscura going away? So it turns out that spectral modeling ends up being very helpful for this with NEXR. There are two types of spectral variability that we are able to capture, and they have very different effects on the shape of the spectrum. In purple and red, we have two observations. They're a few months apart, but they're serendipitously taken while the model for the X-ray power law is in the same state. So the intrinsic X-ray flux has the same shape, and the intrinsic X-ray source, the hot corona, has the same shape and flux. You can see as the obscuration diminishes above about 5 keV, they really do start to overlap. But the column density of the observation in red is much higher, and the ionization is much higher in the pink one. So you end up with this huge difference in the slope of the spectrum. This allows our models to distinguish between a change in the obscuration, which is characterized by the column density, the covering fraction, and the ionization parameter. We also have two serendipitous observations taken while the obscurer is in the same state, again, a few months apart, but the X-ray corona is doing very different things. The corona is much brighter in the blue observation. So this shows that we get a very lateral shift, especially at high energies. It's very distinguishable. This indicates that the X-ray corona is brighter. And we can use this difference in the spectral shape between these two modes of variability to determine what happened during this flare in April of 2021. It turns out here we have the count rate with NEXR reproduced from the previous slide a couple slides ago. And then we have the unobscured flux. This is measured by just taking the flux of the X-ray emission source, excluding from the model the obscuration. The error bars on these are mostly smaller than the width of the data point. And then the ionization parameter is the other thing that changes very dramatically during this period, or during this epoch. And the story that this tells us is that during this part of the campaign, the X-rays get bright and they stay bright for quite some time. This allows the gas to become persistently ionized to reach that state where it gets a higher ionization parameter. The luminosity of the AGN is increasing. And then we see actually during other parts of the campaign that the unobscured flux will reach this state, but not for such a long period of time, not enough that the ionization can really start to pick up and kick in. But during this state, we have a very weak obscuration because the ionization of the gas kind of like saturated, and then the X-rays are also intrinsically bright. Physically, this tells us that the wind is absorbing radiation pressure, which is really exciting for models of how these winds in AGN are accelerated. We also see that during the campaign, the column density of the obscurer changes on timescales of about 100 days. It will increase by about a factor of 10. In purple, this is the column density measured with NEXR. And in blue, this is the silicon-4 absorption trough measured with HST cost and the UV. And this is really exciting because this is the first time that any AGN has been documented in both the X-rays and the UV at this cadence, showing that the X-ray and UV absorption varies together. This was very compelling evidence that this is one absorber. With our collaborators' XMM mutant spectra, you also see these blue shifted absorption troughs with similar velocities, the HST cost, but you can't observe with XMM every single day. So the NEXR observations provide a really compelling look at what is going on in between those XMM observations. We find also that the column density of the silicon-4 absorption troughs are changing. The shape of the troughs changes in such a way consistent with a change in column density of covering fraction. Covering fraction is the UV, column density is X-rays. So what this tells us is that there is this diffuse X-ray obscurer with a large covering fraction, and then these little dense knots or cores of UV absorbing material. You need a much higher density to absorb the ultraviolet, and these are embedded in the diffuse X-ray absorbing medium. Here's my little toy model. And then here are some hydrodynamical simulations of thermal instability in an ionized disk wind. expecting that you would see these, you see the low ionization parameter regions, these blue regions here, we think are the knots that are obscuring in the ultraviolet. And then the fact that we see them move past our line of sight over timescales of 100 days is also consistent with this outflowing wind where there are denser clumps of it that are getting thrown out with these UV absorbers, and then they're moving past our line of sight, and then another one comes up. This has very interesting results in the context of the broadline and continuum reverberation mapping that's done in the UV and optical. I highly recommend if you're interested in that, looking into some of the other AGN Storm 2 papers. A lot of them place the behavior of the obscure in the context of these longer wavelength reverberation results. Finally, with this AGN, we do the goal of our original experiment, which was to search for reverberation between the X-rays and the UV. And the way that we do this is we monitor both the observed flux, this is the actual flux of the spectrum that we see, and then the unobscured flux, which I mentioned is the flux of the emission components of the spectrum, not including the absorption. And then we use the UV continuum as the reference band, and we perform a test using the interpolated cross-correlation function. Essentially, you take a linear interpolation of all of your data points in each light curve, and then you shift your X-ray light curves relative to your reference band. We use the UV as the reference band. And you introduce in your shifts lags ranging from, in our case, plus or minus 10 days with a time step of about 0.1 day. A negative lag, as I mentioned earlier, indicates that the X-rays are varying before the UV. The X-rays leave the UV. This is what's predicted for our X-ray reprocessing. And what we find is that none of our lag measurements are statistically significant. The cross-correlation function here measures the correlation value between the shifted light curves for your given lag that you shifted the X-rays by. This bottom one here is the autocorrelation function with the scan itself. It peaks at 0 days. Makes sense. And then our significance levels here, this is our like 99% significance, 95% significance, the blue and green dashed lines. We measure those with about 10,000 damp random walk simulations. We model each light curve as a damp random walk, and then generate random light curves with those same DRW parameters. And then these independently generated random light curves we'll do the CCF measurement for between the X-ray and the UV. And essentially our correlation here is as good as random. So we don't see any strong relationship indicative of X-ray reprocessing. And a really possible scenario for this is the cross-correlation function relies on something called a transfer function being constant. Essentially that the UV will always, or the response function will always, the UV will always respond to the flare in the X-ray in a given predictable way. It means that the light curves really will be a shifted and scaled version of each other. If the incident SED that the disk is seeing is different than the one we're seeing from our line of sight, because we have this non-homogeneous obscure that is launching from the disk and then passing our line of sight, which is observed at an angle, we're not going to be seeing the same X-rays as the disk is seeing at any given time. So this is a possible explanation for why the correlation is so difficult, or why the correlation is so poor. So this is yet another AGN where the X-ray reprocessing scenario is not business as expected. The next source that we measure that do this test for is Farrell-9. Thankfully, this is a very unobscured, we'll call it a clean AGN. And with Farrell-9, because of this obscuration with Markarian 817, we were getting 1 count per second in a lot of our observations. The faintest observation with Farrell-9 is like 16 counts per second. That's still more than the brightest observation we got with Markarian 817. So we have a much stronger signal. And this means that we're able to use this new and exciting tool, the Scorpion background model. Rather than estimating the level of background brightness that you get from your detector, we're actually able to model the raw observed spectrum and include both our source model. Here we have our power law, here we have our soft excess, here we have the narrow iron K alpha line. Again, we don't include the broad iron K alpha line because you can see we're just so background dominated in a lot of these observations. You don't get well constrained current parameters for it. And then you also now model the sky X-ray background, the optical noise peak. So you have optical light that can hit the detector and produce a faint soft X-ray signal by producing currents. And the brightest of the background components, the particle and other non-X-ray backgrounds. So you have other high energy things hitting the detector and producing an electrical current. We model all these simultaneously, which means we're able to account for uncertainties in the background. And we are still able to measure changes in the power law and the soft excess. Now, the shape of the power law index gamma, which denotes how much of the emission comes from the soft X-rays versus the hard X-rays, the slope of this curve, and the flux of the soft excess are degenerate. You can get a very bright soft excess, and then your model can compensate with a hard power law or vice versa. And so when we try to leave both of these free in fitting, the power law index and the soft excess flux, we end up with a physically useless result. There's like the soft excess is just noise. We end up seeing that the soft excess is about 10% of the brightness of the total spectrum. So it's in your chi-squared statistics, you get dominated by the brightest, loudest source. We mitigate this by fixing the power law index to the median value from the run where everything was free. And interestingly, now the soft excess is mimicking UVW2 in a very cool way. This is the correlation between the UVW2. Here's more ICCFs. Get ready. That's the rest of the talk. The correlation here is the strongest that's ever been recovered from an X-ray band and the UVW2. The soft excess flux is correlated with an R value of about 0.82 and a negative lag, indicating that the soft excess leaves the UV, which is what we would expect because this is coming. If this is either the warm corona or the relativistic reflection, it should be far interior to the UV disk. The other thing that we do now to account for the variability that should naturally occur in the power law index as it is responding to changes in the available speed photons from the accretion disk is we follow the assumption that underlies a lot of UV optical reverberation mapping experiments, which is that the variability pattern in your reference band is essentially the same pattern that you're seeing in your other disk observing bands. Anything that's observing the disk, you expect to see the same variability. So we fit a function that includes a scaling factor, right? How much UV flux corresponds to how much soft excess flux in any given observation, and a lag. So we shift the function to predict our soft excess fluxes. And we do this over a grid of scaling factors and lags. This paper, I'm happy to say, got accepted to AppDay last week, and it just came on arXiv today. So if you want to learn more about the methods, definitely I would love to chat about them. But we find with this method an improvement in our fit over the entire set of observations. So allowing the power law index to vary really does improve our characterization of the AGN. And we find a negative lag where the soft excess is still leading the UV. So the correlation between low battery power law and the UV is still very weak, in R of about 0.5. And this is really a challenge for the X-ray reprocessing scenario once again. In the scenario posed by X-ray reprocessing, the X-rays are driving all of the variability in the UV. And this could possibly still be the case if there's some sort of issue with the transfer function, right? If the ICCF is not a super reliable measurement of what we actually expect to see in the disk. But the X-rays have to have enough variability to power the variability that we see in the UV for X-ray reprocessing to occur. So what we see from this geometry is that, first of all, our high correlation between the soft excess and the UV suggests to us that the soft excess is linked with the accretion disk. It's undergoing these same slow temperature fluctuations that I talked about earlier. Specifically in the first 300 days, there's this slow trend that we see in both the soft excess low battery X-ray power law. And then this warm corona idea that we get from there is that the soft excess is basically these electrons that have left the outer layers of the accretion disk and have formed their own warm corona accretion flow. This has also been suggested by previous spectral modeling in the X-rays and SED modeling for Farrell 9. But with this high cadence observation technique, we're able to sort of actually constrain the location of the region for the first time. The theoretical prediction for where the UVW2 emission should lie comes from parameters such as Eddington ratio, the conversion efficiency for accretion, like accreted material to light, the mass of the black hole, and all of these parameters give us an estimate around 60 gravitational radii away from the black hole. This is where we expect the peak emission from the
Low battery
to be arising. But our lag that we got between the soft axis and the UV suggests that there's 81 gravitational radii of light travel time between the two regions. So this is where we get our idea for this tall warm corona, this secondary reprocessor that has a height of gravitational radii, possibly even taller than the warm corona or the hot corona itself in purple. And linked again with the whims and temperature fluctuations of the year. So I mentioned that we also want to test if the X-rays have enough energy to power the variability of the UV, to see whether there really are these intrinsic disk fluctuations that are producing this strong correlation between the soft excess and the UV. We use a measurement called the mean fractional variation. This depends on the sample variance, the mean square error in our observations, and the mean flux. And this is expressed as a percentage. So we would say that
low battery
UV2 has a variability of about 25% around the mean. And then the X-rays have a variability of around 18% in the power law. Now, this could be fine if the X-rays are inherently way more energetic than the UV. You could still see the X-rays being having a much lower mean fractional variation and power than UV. But what we find from previous ICD modeling of the source is that the X-rays only contain about 23% of the total power in the SED. The rest comes from the disk. And the UV is towards the inner disk, so it's a very good proxy for the amount of variability we're seeing. We expect the innermost part of the disk in the extreme ultraviolet to possibly be even more variable. But we simply do not have enough energy in the hard X-rays to power the variability in the UV. So putting this all together on very slow timescales of months, the X-rays and the UV are doing separate things. We're not seeing the UV variability driven by the X-rays, and we're seeing this relationship to the soft excess that suggests a warm corona. In the fast part of the variability, if we take a boxcar average with a width of 30 days and then subtract that boxcar average from the actual light curve, these are our residuals. And we see that there is a region on timescale shorter than 30 days. The X-rays are variable enough, even with their 23% of the SED, to power all of the observed variability in the UV. So there's this overlap of slow and fast variability that makes up our full light curve. The correlation here is really poor between the X-rays and UV, but recent work has suggested that if your corona is changing dynamically in height or energy density, you're not going to get that even response function for the whole campaign that is assumed for the ICCF. So it is possible energetically for the X-rays to power the UV, even though our correlation is not strong. To sum all these up here, you can see the threshold where the energies are comparable at 30 days. And then on very long time scales at about 150 days, the correlation actually peaks between the light curves at about 0.9 R value. So we are finally seeing the slow seed photon behavior, we think, where the X-rays are being fed by increases in the flux of the UV emitting disk. Just on this timescale window of about 30 to 150 days, this is where we get into the more novel, exciting temperature fluctuation physics. Our final AGN is the most well-behaved golden child of the sample. NGC 7469 is unobscured, and the soft excess in states where it's low in flux and high in flux, it has a much closer flux to that of the power law. It's much brighter relative to the total amount of flux that we're seeing. And so that problem with the degeneracy that plagued Farrell 9 is not a problem here. If we let both the power law index and the soft excess flux vary, the parameters are not well correlated with each other, and they're both independently constrained.
So this is very exciting because we're able to put the whole picture together, and we see that here the X-ray power law and the UV are actually pretty well correlated. Their R values peak at around 0.8, and the lags are consistent with 0, which is what we expect for this very small 0 days, what we expect for this very small region of the disk that should be much less than 1 light day. Our sampling cadence here actually starts to be the limiting factor. We observe with NICER about every day, and these lags that we're measuring are shorter than a day. So you can't say with a lot of precision exactly how close the X-rays and UV are to each other, but the very strong correlation suggests that these peaks in the X-ray light curve, these little like bunny ears here, I call them, these are inducing a response in the UV through reprocessing. And then the soft excess is also well correlated. On slow timescales, we see this slow change in fluctuations indicative of the seed photon behavior that we expect for Comptonization. And the X-rays actually have enough variability to power all of the UV variability here. So there doesn't seem to be this separate intrinsic UV variability component that is driving the light curve, so to speak. It can all be explained by the X-ray variability incident on the disk getting reprocessed. We also compare the correlation between the soft excess light curve and the power law flux, and we see the strongest correlation in any of these campaigns so far of about 0.9. The lag is very small, consistent with 0 days, and it is within its maximum distance spans the upper limit set by a much more precise timescale reverberation mapping experiment on the broad iron K alpha line of this source. So here, because we see this very strong correlation with the soft excess and the X-ray power law flux, and we know the X-rays have enough energy to power the variability that we see in the soft excess, this tells us that this is actually a really good candidate for that relativistic reflection scenario. We know some relativistic reflection is happening because we have a broad iron K alpha line, and it seems here that the majority of the emission in the source, in the soft excess, is coming from those blurred ionization lines at soft energies. So here we have the theoretical prediction for the UVW2 disk. As I mentioned, this is kind of right at the, just like with the soft excess, our measurements are not super precise in the time domain space, but our measurement is compatible with the lower limit on the theoretical region for the UVW2 emission to arise from. So in conclusion here, using our NICER spectra in combination with Swift UVW2 monitoring, we're able to capture daily snapshots of the X-ray spectral variability in these AGN. This tells us that our we can observe changes in obscuration, and we can observe changes in the separate emission components of the hard hot corona and then the warm corona or relativistic reflection in the soft excess. Sometimes the X-ray emissions are not well correlated with the AGNs, with the UV. This tends to depend on what AGN you're looking at. And this can be due to obscuration that is different along our line of sight versus the line of sight incident on the disk. This can also be possibly due to if you have an optically thick corona that is blocking the direct reprocessing between the X-rays and the UV. This would mess with your reverberation signal or any sort of dynamic changes in the hot corona's structure or energy density. But then I think almost the most confusing of all is that sometimes it does work exactly as the idea for X-ray reprocessing predicts. So there's no homogeneous description of the inner accretion flow of the AGN in these 3 samples. Sometimes there are winds, sometimes there's the warm corona, and sometimes it's very clean along the X-ray UV line of sight. So those are the first sources that have been measured like this with NICER. My hope is that we continue to expand our sample size and try to find some sort of underlying thread that is linking these types of AGN behavior. So I would be happy to answer any questions at this time. Yeah,
Yeah, hi, can I, I'm lost with Feral 9. Can you go back, please, to your, slide about the delays between X-rays and the UV, no, and the, soft excess, please? No, it's a bit,
Mhm.
I'll come back to that actually a bit later. Yeah, here, no,
Yeah, there.
Yeah, right,
Mhm.
so I don't get it. First of
Sure.
all, does the soft excess, follows the X-rays, the hard X-rays?
No, it ends up following more strongly the UV than the
But it
X-rays.
feeds the UV.
Yes.
First, that.
Yeah,
right?
yeah.
First of all, the signature of X-ray processing is the fact that the UV, the optical will follow one the other.
Mhm.
That's the signature, because when you have X-rays, you
Mhm.
have strong reprocessing of the disc.
Mhm.
And the UV will not exactly be like X-rays. X-rays will be up and down like
Mhm.
crazy, and the UV will be very, very smooth. So that's the signature of X-ray reverberation. And actually here, the Rick Edelson paper recently just showed that indeed UV comes first and then the others follow, right?
Yeah.
There's no indication of fluctuations moving inwards, nothing, right? And this is on very long time scales because you have here light years of 2 years,
Mhm.
right? There was one indication at the beginning, but there, the velocity to go from the outer disk to the intake was tiny. There is no physical way that you will have propagations as you are talking about moving inwards there, right? Okay. The time lags, the negative time lags are too short. Plus, this is not the correct equation to do reverberation, right? We have published with Elias Damon, with Michal Dosia, a few years now, the correct equations for reverberation. Where is here the height, the corona height in this equation?
Yeah, this one assumes a static corona
Where's the
height of about 10
Because the
gravitational
time
radii.
will depend on the height.
Mhm.
Where's the height here?
It's not included in this one, like I mentioned, this one has
Where's
a
the black hole spin here?
The problem with including things like the black hole spin and the height here is we're not sensitive to the height of the corona or the black hole spin in these
Oh,
measurements.
yes, you are. You are very, very, very sensitive because the time lags depend critically on both the time, on both the height and the speed. So you cannot really come here and tell me that the time lag actually comes and tells you that this comes from an annulus. It doesn't. For example, the optical, the V band, it comes from the innermost. It's a black body. It's a broad emission. And actually, the flux is to the power of 4, temperature to the power of 4. Most of the UV comes exactly at this scope because it's so bright. It's not an annulus. You cannot use this equation and claim that you have a delay that will actually tell you this thing is at this radius. It's wrong. It's not correct. We have been publishing this quite a few years now. And Panagiotou, who is in our team, actually just showed you that indeed you cannot look at X-rays and UV. They're doing different things, and yet it is reverberation. You have to look at what the UV and the optical do.
Then
Exactly.
if
That's
it is
exactly what
all
happened.
explained with the reverberation, how would these models explain the fact that there's not enough energy in the X-rays
So
to
can I
power
see
what we
the spot,
see?
the Hagen and
Mhm.
Brown paper, please?
Yeah, absolutely.
Sure.
I think it's,
How do they get the break, the energy brain, the high energy brain there? They don't have the data.
this is true. They don't have the high energy data. They end up fixing it.
Exactly. If you change it, you have lots of power. So this is a hypothesis. This is not fact.
What
They
I
don't have new star. Actually, they do have new star data, but they didn't use them.
So what I
Right.
did to test the range of the high energy power law cutoff was in the paper, this is included in the section where I talk about the energetics. The Lofink et al. Paper on Farrell 9 shows
That's a past paper.
it
right?
uses new star.
Yeah, but that's
like-
not that campaign. It's
No, it's a
past.
past, but what I'm
Exactly.
saying is the power law cutoff in that campaign, the upper limit is about 900 keV, which I think you would agree is much higher than the limit that they use in the Hagen and Dunn paper.
Yeah.
And we calculate the uncertainty, it's a few percent in what the total X-ray flux in our model would be using a a cutoff energy of 900 keV.
What drives your variability is the total X-ray flux. The
Mhm.
total X-ray flux depends on the E0, the lower cutoff, which you don't know.
We don't
And
know
you
that.
don't know because you didn't do the proper spectral fit to find out. And that's Kim said. And the high energy cutoff, both of them, right? It's not just the the high energy cutoff, it's the low energy cutoff as well. And you don't know it.
That is true.
Exactly. So it's an assumption.
It is an assumption. In the
Okay,
paper,
so
we talk
it may
about,
be wrong.
yeah, absolutely.
Exactly.
Yeah.
That's what I'm saying.
In the
Good.
paper, we talk about
Good.
that, of course.
Exactly.
Yes,
Good.
we definitely, we measure that, we talk about the fact that we don't have, we're not sensitive, right, to the low energy cutoff. In Kin said,
This
it's
model
an
is
assumption.
completely wrong because you don't see the propagations coming in. Ederson showed the cross correlation.
Mhm.
The correlations, the variations start from the UV and they go out.
Mhm.
There is no propagation. This is a wrong model. The Hagen and Dawn. It's clearly, I can't believe it.
Have you looked at the Neustadt and Kachanik paper where they show the temperature maps and they show that the temperature maps sort of flow in and
Would you
out?
like to discuss them perhaps later, and I'll show
Yeah.
you the real temperature maps.
Yeah.
Where you do relativity.
Sure.
Kachanik, they don't do relativity, right?
Mhm.
And the maps could be entirely wrong. So I would be very happy
Yeah,
to
yeah.
discuss with you and show you some real maps with relativity. in it.
Sure, I would
Let's
love to see that.
Fantastic.
Yeah, there's a huge amount of assumptions made in the spin of the black hole in
No, there's no
the,
spin in the black hole.
in the, in the
I'm
other
sorry.
paper, in NGC 7469, we talk about that as well. The fact that like the SED model is completely different based on the spin. Like I see where you're coming from with these concerns. We're very limited, in the assumptions.
We have models that take into account spin. I'm sorry. It's not a concern.
We can talk about-
do
yeah.
have models that take into account spin. So I don't want you to misunderstand me.
Yeah.
What I'm saying is that we can take into account spin.
Okay.
That's what I'm saying.
I'm interested in talking about this with you. I think with
Sure,
Feral
that's
9,
fine.
with the Nicer campaign, we're very limited on what we can model without overfitting the data, right? We use specifically a black body for the soft excess, not because we think it's a black body, but because that describes the fit with a few number of parameters. But yeah, I would love to talk to you more about the more advanced
Sure,
models that
sure,
you've been working on.
absolutely, anytime.
Are you Yosef Papadakis by chance? Ed says hi, by the way. He asked me to say hi when I got here. So yes, I would love to talk about this stuff more with you, and I appreciate you.
Actually, it would be great to have it, you know, so
Yeah,
it would be-
absolutely.
Absolutely.
Cool. All right. Anybody else?
Maybe a sort of thing, when you were talking about the obscurer,
Mhm.
can you also estimate distance in which this is happening?
Yeah. So the distance is modeled in so we don't estimate it in our paper, but work on the XMM Newton side by Fatima Zaidouni and Colin Lewin. They're later on AGN Storm 2 papers. They look at the continuum delays and how the continuum delays respond to changes in the X-ray to kind of say like what the launching time scales are. And they think they're on the order of like 100 days, which is kind of consistent with the scales that we see for our actual like column density curve. And then from there, they calculate what they expect the height from us to the disk is. The paper I think is still in revision. Last I read through it. So I don't want to like quote an exact number. But I also don't remember it off the top of my head, but the Colin Lewin et al. Paper on continuum reverberation with AGN Storm 2, and then the Fatima Zaidouni paper on the XMM Newton observations both talk about kind of the distance scale. We think it's 3 light days away from the black hole, but then how far up it gets before it gets to our line of sight is maybe kind of what you're talking about.
Okay, so there's another question. Let's